All right, welcome. Today we're going to be talking about function rules and some applications of functions. So these are called function tables, sometimes input-output tables. So a function is where we have an input value, it goes through a rule, and you get an output value. And that rule is the same for every input-output. So no matter what you put in, it's going to go through the same process to get the output. So we're looking at this. So the key here is to look for patterns. Okay, a lot of these are going to be our linear functions because that's what 8th grade math is all about. Some 7th grade math too. So what are we doing to our input to get our output? So as I look through number 1, it looks like my outputs are 2 times my inputs. So my rule would be 2n. All right, this time my input, let's see, we get put in 5, out comes 1. Put in 6, out comes 2. Put in 8, out comes 4. How about n minus 4? Does that work? It sure does. All right, this next one. Okay, I'm seeing kind of a linear pattern. My output values are going down by 3. My input values are going up by 1. So to me, that looks like a slope of -3. Then if I worked backwards in the pattern, my y-intercept would be -1. So I'm thinking this -1, not 0. So is it -3n minus 1? So if we think it's that, let's double check. Let's plug in some of these. So as if that would be -3 minus 1 is -4. If we put in 4, that'd be -12 minus, yep, that's the right one. So -3n minus 1. So use what you know about patterns and about linear equations, and that's what you're going to run into. All right. Ooh, looks like here we're going up by 2s on our output, up by 1s. So this looks like we are just, if we worked backwards here, we'd have a, come on, pencil. We'd have a 0 there. This would be a 4. And our slope would be 2. So is this 2n plus 4? That would be it. Okay. So the output is like your y. Your input is your x. Okay, so that's how those work. Now let's look at some application problems. Gina wanted to study how the area of a rectangle changes with the length of its side, or its length if its width is fixed. So the width never changes, but she's going to change the length. She computed the area of several rectangles that had the same width and different lengths. She then plotted the results and connected them with a line as shown in the graph. The graph shows the area versus the length. Find the range and the domain of the function. Okay, so we got to be careful. It lists the range first and the domain. The range again is our y. The domain is our x. Okay, well, because that line is continuous, we're starting at 0. So that means our range is going to be 0 and above. So we could write this using an inequality, saying we want y to be greater than or equal to 0, 0 and above. Is there a limit to when it ends? No. And then domain is our x values. So that would be, again, there's no limits on that, other than we're not going to be negative because we're talking side lengths. So we want x to be greater than or equal to 0. Sorry, that's not a very good greater than sign. Okay, or you could use like a verbal description. That would work too. All right. A machine at a bakery poured out flour for 16 minutes. At the end of that time, the machine was empty. The graph shows the amount of flour remaining in the machine versus the time. Find the domain and range for the function. Domain and range All right, so domain is all our x, so our time, because that's our x-axis. So we started with 0 time, and how long till it emptied? 16 minutes, and time is continuous. So our domain is going to be 0 and 16. We want x to be between that, and the way we represent that is using what's called the compound inequality, where x is sandwiched in between. Okay, that's saying x is greater than the 0, but less than the 16, because look at the inequalities. That's exactly what it's saying. Okay, now the range goes from 0 to 800 and is in between those values there.